Good. So welcome everyone to today's seminar. Today we have Inteli from our school, from computer science department, and he's going to talk about differential privacy. And before Abel introduce the speaker, I will just remind you that if you have any questions in the talk, you can use three ways to ask the question. You can either use the chat, or you can type your question in the Q&A, or you can make use of the function that raise your hand, and then we will allow you to speak. Now I will just pass it to Abel.
Thank you, Yanchi, and it's a pleasure to have Jintat here with us today. Jintat got his PhD from MIT in 2016. After that, he spent a little bit of time, I believe around a year at Microsoft, and then he came to UW, where he's currently an assistant professor. Jintat has won a number of awards, including a Career and a Sloan Award, and he's one of the co-PIs in the Institute for the Foundations of Data Science, which is this institute that NSF has just funded that goes across 4 institutions, and in which University of Washington is the lead institution. So Jintat's work actually is in many ways very statistical in nature. So I think that his presentation here will be, I think, of a lot of interest for many of us. So thank you, Jintat, for being with us, and welcome.
So this talk is basically just, you can think this is more like a lecture than a seminar. So today we will talk about differential privacy. So the talk outline is something like this. I will first try to convince you this topic is important, then give you a basic definition. Basically, the majority of the talk is just about why it's important and the definition. I will be very happy if you fully digest the definition of differential privacy. After that, then I will give some algo and some theorem. So I will first explaining why this is an important topic. As we all know, a lot of organizations need to handle a lot of data, and how to handle the data privately is super important. For example, in Europe, they have some data protection law. They can fine a company up to 4% of the worldwide revenue. Or more concretely, for example, Facebook a few years ago have the Cambridge Analytica scandal, and they have been fined for $5 billion because they leaking user information. So this is a problem that is very important in very concrete sense in terms of money. And conventionally, people use different ad hoc approach to protect the privacy. For example, you can control who can access the data. You can control what kind of purpose people can use for the data. For example, in government like census, then they can control, for example, only researcher can read the information in details. Or for example, for medical data, then they can only release to researcher. Or there is another approach is you have a bunch of data, you want to release it, then one way is you just remove the name of all the data. Then maybe you think that is safe enough. Or another way is you come up with some very careful way to hide your information, and then you release the information. But turns out usually if you try to protect your information using an ad hoc way, usually there could be some leak. I will give you some example for that. But inherently, you should think whenever you provide a statistic to people, or maybe you build a service based on the data, then in some sense you must leaking some information. And one important thing about differential privacy is to quantify how much information you're leaking. Just give you a very concrete example. This is copied from slides from Census 2020. In Census, they usually, for example, you can think in each zip code, they try to measure how many female, male, or different races people in there, and maybe they want to release what is the average age among female or those kind of information. This is a concrete example. You may thought this type of release is very safe. Namely, we didn't really tell you what kind of people inside. But turns out if we are just given this table, this is a concrete example. Let's say we are given those numbers. Then turns out you can, by solving some equation, you can recover all the information in that area. And more, this is just an artificial example. And what census did is they try to go back 10 years ago. They have done the 2010 census. They have collected all the US citizens, the age, their sex, race, ethnicity, and relationship. And they release a bunch of statistics. So what they did is they try to ask, can they use those statistics to recover all the information about all the person? And turns out they are able to recover half of the population. So this is a really huge leak. And this is the reason why they need to do something less ad hoc for the next census. I mean, this census 2020. And one thing to remind you is, even for the last census, they are already doing something to protect the information. For example, if for a certain county, they have too little people, then instead of releasing this is 4, they will just release it small, or some number to represent it small. But turns out even those ad hoc measure is not enough to protect the data. And this year, they are really releasing the data according to the differential privacy. Beyond government, company also need to handle a lot of data. For example, what app you use, what website you go to, or what the test you type in your message. And they are super useful for providing service. For example, app data can use to suggest new app to you. Browser history can use to suggest the next website you want to look. Or for example, test data can use for test prediction. And you certainly don't want company to release your data in privately. For example, I heard this is a real story. Someone tried to use the test prediction to take out some credit card information from Apple, and they are able to do this. I don't know how they do it. So this is a real issue. And for company, usually they are not releasing statistics. Instead of, they use the data to provide service, and those services usually can still leak private information. Here I give you a concrete example. This is regarding AOL internet company released a search history of user. This story is in 2006 August. And 5 days later, researchers realized those data, although they delete all the username from the data, they can still recover from the data who are the user. You can imagine how to do it is pretty easy. Not just AOL have this problem. Netflix also did this mistake. Netflix released a bunch of data about each user, which movie they like. They again remove the name of all the data and thought that is secure enough. And turns out by combining this with some public data, they are able to match some of the user their rating. Both story have some similarity. Is usually if you only have the data, it is kind of difficult to recover the name you remove. But the problem is usually you have some side information. For example, for the Netflix data, the side information you have is the IMDb. And when you have side information, usually it is pretty easy to recover the data. And those stories just telling you ad hoc information, ad hoc measure to protect privacy usually is quite unsecure. And the real trouble is we have side information to do the attack. Beyond the problem of side information, the other problem is usually when you release data, you are releasing data from many people. And for the attacker, they usually only need to attack a few person. For example, if you are a hacker, you want to find people credit card information, it suffices to successfully attack few people. So you really want to protect the data really well. And the other problem is usually when you release data, you are releasing a lot of data at the same time. And usually a lot of data in Python is easy to recover the identity. For example, using zip code, birthday, and gender, you can easily identify half of the US population. So in some sense, protecting data is inherently difficult. And one thing differential privacy try to do is we try to come up with a way to avoid people attack your data even with the side information. But you may wonder, how can you model side information? It is something very abstract. And turns out you don't need to model that and still able to protect against those attacks. So I will now move on to the definition of differential privacy. And just to repeat, the purpose of differential privacy is to promise you will not be attacked even no matter what kind of other side information people have. This concept is introduced by Cynthia in 2006, and gradually it becomes the main concept in the privacy research. There is thousands of follow work with many awards, and most importantly, it is currently employed by something like Apple, Microsoft, many big companies, and also by government. So I will now explain the definition. Remember, our purpose is to defend against side information. So what is the worst scenario? Imagine you have a database. You want to protect, the information about. Then what we assume is the attacker know all the information in the database except about. So we assume the attacker know everything about the database except the record we want to protect. And the second key concept is we assume you always certainly you cannot just release the database. We will process the database by some algo. And we will assume your algo always output a random output. For example, let's say you have a database of age. Yeah, let's say this database is the age of faculty in UW. And let's say you just release the mean of the age. And let's say you know every faculty age except about, then do you see the trouble? Then certainly by a simple formula, you can recover the age of him by just doing some subtraction. So in general, if your algo, we put a deterministic output, then if you know all the information except one guy, then you can use the output to recover the last person. And that's why in differential privacy, it is very important. All the algo we are talking about only output a random statistic instead of a deterministic statistic. This is very different in traditional statistics. Usually all the estimator is deterministic, it is just some formula. But for DP, it's very important you need to output a random estimator. So what we want, and we call output is differential private. If imagine you have two databases, D, let's say D is this one, D is without a bell and D prime is with a bell. And you run your algo, you get some output. Remember, both output is random. And you can think both a distribution of output. And we call this algo is private if these two distribution is similar when you remove one person. So formula is this. we call an algo M is epsilon differential perfect if for any two labeling database, labeling means you remove a person. For any two labeling database and any set of output S, you look at the output on D prime, it is on a set with the probability of the output for D prime is approximately equals to the output of D. To give you an example, why this property is important. Imagine this database D has a bell, and this database has a bell, and then the algo output something, and then someone looked at the database and they recover some information about a bell because of the output. Then a bell can say, no, it is impossible, because whatever the output for D prime, the algo can output the same with almost the same probability without me. And that's why you cannot really sure from the output of the algo that you know something about me. Yeah, I will stop a little bit here. Anyone have question about this definition? I give you, maybe I give you a example here. Imagine I have another definition. Why my pointer is smaller? Imagine if I define the differential privacy differently in this way, instead of asking them to be multiplicative, ask them to be additive. Or maybe I should give you rough sense what is the epsilon. People usually pick this epsilon to be constant. So you can think it's something like 2. Oh, I saw a question. How does help attacker? Oh, so okay, someone asked how does differential privacy help the attacker guess when, okay, the question is, if the attacker only need to successfully guess a small amount of time, then how differential privacy help? So let me give you an example here. Imagine if someone gives you an alternative definition of differential privacy. Instead of additive instead of multiplicative is additive. Anyone see any issue about this definition? Imagine the database is just a bunch of credit cards. And then what the M doing is you randomly sample a credit card information and output one of the credit card. One of the credit card number. Then what happens is, if your two labeling database, you didn't remove that credit card, then two output will be same because you didn't output that credit card. They are only, you only affect the output if turns out the algo really pick your credit card. So turns out you will off by additive number that is 1 over the number of users there. But at the same time, they are not multiplicative at all. Let's say your credit card number is 1, 2, 3, 4, and all other people, the credit card number is 1, 2, 3, 4. Then what you can do is you put in S is 1, 2, 3, 4. Then you look at, say, D prime is the database with U, D is the database without U. Then you look at this quantity, the probability the algo output the critical number 1, 2, 3, 4. What is that probability? Because we know all other people does not have that credit card, so the probability here will be 0. How about this, the left-hand side? The algo only output the credit card 1, 2, 3, 4 only if turns out the algo pick out your credit card. Say there's n people, so this will be 1 over n here. So 1 over n is not a multiplicative approximation to 0, but it is an additive approximation of the 0. So you see additive is kind of problematic here. And the reason why we want multiplicative is we can say whatever the algo output, it can output without you. And that's why you can always deny any conclusion you can gather from just the output of the algo. Someone asked why this is exponential. This exponential is not important. You can define it to be, for example, 1 plus epsilon instead. But it is easy to check. This definition only makes sense if this number is larger than 1. So there is no inherent reason of using exponential here. Any question about this definition? Okay, I will continue. Wait, why? Let me go to, oh, I know what happened. Oh, wait. Oh, I accidentally used, okay. Okay. Wait a moment. Yeah, remember, algo can only be differential private if the algo is random. So the output of the algo is always a distribution. And you can think when we call it differential private if the output for a labeling database, the distribution is multiplicatively similar. For example, that 2 distribution is multiplicatively similar, is off by a constant-ish. But for example, this one is not. Can you see why they are not multiplicative approximate? For example, you look at this output here. This output here, in here, the probability is 0. So they are not approximate each other. So one important thing about DP is when the algo outputs something about D, then it must output this something in D prime with some probability. Otherwise, you will break the privacy. Also, this is again highlighting privacy. In some sense, under this definition of privacy, it's saying no privacy is possible if you don't have randomness. So now let me give you a very simple DP algo. Let's say you have a histogram of age and you want to release this statistic. How you can release? One way you can do is you just add a noise according to Laplace distribution. For example, origin is here. You just add you just randomly sample a number according to a Laplace distribution and output something here. You do it for every bin, and you will get a new histogram which is differentially private. So just as an exercise, let me prove you this is differentially private. Remember, according to definition, to prove something is DP, you need to prove in this way. You need to prove for any output. Let me see. Is the definition equivalent? Someone asked, is the definition of DP equivalent to bounding the density ratio of output under every? Yes, someone asked, is the definition of DP equivalent to bounding the density ratio of every pair? And yeah, that is true. Okay, yeah. So to prove this, you fix any output of the algo S. And let's say the output is set 1 to set D. And again, we consider two labeling database D and D prime. And what we want to compute is the probability the output is set in D prime compared against the output is set for D. Because our algorithm is just adding Laplace noise independently, so the probability is just product of each output. And one important observation is, remember the algorithm is a histogram, so changing one data can only affect one of the bin. So you just need to focus that bin. And for that bin, the probability is just given by the Laplace density exponential to something. And then because removing one person can only, here, A is the origin statistic, X is the noise we're adding, and Z is the output. And we adding a person can only change the statistic by 1. So the ratio of that two distribution will be just bounded by one of the term, which is 1. So you get X e to, oh, I guess this should be plus, otherwise it doesn't make sense. So the ratio is exponential to epsilon. So this is just an example. And one thing to notice is how much error we introduce in this algo. It is roughly 1 over epsilon. Okay, how do you make sure this? The data is yeah, someone asked how can you make sure the output of the algo is still good enough for the purpose? Yeah, in general, this is a main question about DP. I mean, for some problem, turns out it's very easy to come up with a DP algo that the output still makes sense. But sometimes it is very non-trivial to come up with such algo. And even worse, for some problem, it is impossible to come up with a DP algo that produce any useful information. And in that case, then but you should always think this is a trade-off. For those impossible case, then in some sense, then you need to tell the user you need to release the information in some sense. Yeah, for example, for this problem, then we know this is just a trade-off. If you want the privacy epsilon, you can think epsilon is the privacy. Smaller mean you are protecting more privacy, and in that case, your error will be larger. It is always just a trade-off. And how much you are willing to sacrifice the privacy depends on the company policy. And turns out what we told you before is more generic than just releasing a histogram. Imagine you have a statistic F. It is a function from database to say out D. You want to release a statistic of length D. And we define the sensitive of this statistics to be this, to be how much the statistic can change if D and D prime is the labeling database. We are measuring how much it can change in L1 norm. And then turns out what you can do to release F privately is you just add a Laplace noise for every coordinate. With the coefficient in the Laplace noise is the sensitivity over epsilon. And basically by the proof same as before, this is epsilon differential private. So this one is saying whenever you want to release something that is robust, then usually you can do it privately. So there is another definition of differential private. We call our algorithm is epsilon delta differentially private. If it is the same definition, except beyond the multiplicative, you also have an additive term. But remember what I just told you. In order this definition to make sense, delta should be very small. Otherwise, in some sense, you could be just releasing a random user information. So usually in practice, you want delta is much less than the size of the database. Otherwise, it doesn't make sense. Yeah, let me give you, and in some application, this delta term is necessary. Let me give you a necessary example for that. Let's say this application is test prediction. You have a bunch of tests. You want to collect the 2 gram in 2 word. From the user data, you want to collect a bunch of 2 words. For example, maybe usually people type dot after cat usually. So you in your test prediction, you want to predict dot after cat. And what we want to do is, let's say we want to collect a histogram of 2 pair of words. And the question is how we can do it in differentially private way. This time I will not prove anything. I will just give you the algo. So what you can do is you just collect you just first create a histogram of all possible pair of words. So you can dot, cat and picture, and a barrel and statistic. And again, we add a Laplace line for every statistic. And one thing we need to be careful is certain statistic doesn't happen a lot. For those statistics, in some sense, if you release this pair of words, then you are kind of releasing some information. So what the algo do is you pick a threshold, and whenever the count is less than that threshold, then you remove that data. And then you can release the histogram after you removing all the small bins. And what you can prove is this algorithm is epsilon delta. And one thing I want to emphasize is this algo have delta larger than 0. And this is necessary because, for example, for this bin, remember what we do is we add the Laplace noise. And the Laplace noise always have non-zero probability of adding a huge number here. But we know it add this number with exponential small probability, but it will happen. But when it happens in that way, then we are releasing this information. But imagine if the database does not have this pair, then the algo will never add noise there because you cannot eliminate all the possible pair of words. And that shows with some small probability you release this pair that you wouldn't release if you don't have that user. And this is why this delta is larger than 0. But this is okay if that delta is very, very small. It is saying we almost never leak information about user. So that is still okay. Yeah, this example also show, for example, in census, we also have similar situation. And previously, people release histogram by just look at all the statistics. You just release the information when the count is larger than k. And it is easy to argue that it's not private at all, especially if you know all the information about all users except one in the database. So in practice, what kind of epsilon and delta we should choose? This is kind of funny. Although in the definition, this is epsilon e to epsilon. So you could think, but in practice, people usually pick some epsilon pretty large. For example, in Apple, they choose epsilon to be either 4 or 8. Something pretty large. You imagine e to 8 is a huge number. But the reason people choose such a large epsilon is because it is kind of a trade-off. If you pick epsilon too small, turns out they cannot really get any useful information. I think in census they pick epsilon to be 6, somewhere between 2 to 6, depends on the application. And delta, usually people choose something less than 1 over n. After people define differential prophecy, people ask for many problems, can they do it perfectly? And currently there's many problems we know how to do it in DP way. And this is still have a lot of open problem and a very active area. The real benefit of why this is a good definition is this gives you a very concrete way to measure privacy. For example, you can prove math about it. For example, you can prove something like this. You can prove post-processing does not affect privacy. Imagine you have an algo that is epsilon delta private, and you have a post-processing function t. Then you can easily prove if you have a database, after you run it by M, and then you get a statistic, and then you do some post-processing, it will not have the privacy. And for example, you can prove something like this. If you get K statistic, you will increase the privacy loss by square K factor. You can think this is just proven by chain of bound. Precisely, if you have K algo that is epsilon delta private, then outputting all the statistics at the same time will be roughly square K epsilon, comma K delta private. Here is another interesting theorem. Let's say you have a very large database. What you do is you first sample every user by probability P, and then you have some algo to produce a statistic. And let's say if this algo is epsilon delta dp, then you can prove this whole procedure is epsilon p delta p dp. This is kind of important. It is saying if you have a problem that you can produce a pretty accurate statistic by sampling the data, then usually you can get a DP algo because you can first sample down the database and then do something more simple there. And even though if that algo is not that the epsilon delta is quite large for this algo, the epsilon delta for the whole algo is way smaller because you have done a sampling. So now I will give you a kind of a universal algo for differential privacy. So this is very generic. Let's say you have a statistic. You have a statistic, say you from some database to some output. We measure how good is this input output by a function u of d, and output measuring how good is this output for this database. For example, one way is let's say you have a statistic SD, and then you measuring how good is the output by just just L1 norm, let's say this. But in general, you can be any function about input output. And let's say this utility function is robust. Namely, if you change one of the user in the database, the function U doesn't change a lot. Then turns out you can output the statistic by this way. Because this algo is exponential mechanism, the algo do this thing. For the input D, the algo will randomly output output O with probability proportional to exponential something times U of DO. Namely, it will output, the output there is better with high probability. And you can prove this algo is epsilon 0 dp. So this is almost saying almost anything can be made differentially private, as long as you're measuring how good is the output in a way that is robust. And if you think about this more, turns out this is just doing a Bayesian sampling. To be more concrete, let's say you have a bunch of data di and you have a model with parameter theta. And let's say the model happens with probability p. Then the lateral utility function you can define will be just the log probability. Because the parameter is better if the model predict it happens with high probability. And we define, and then the sensitivity is in some sense measuring the Lipschitz constant of the log probability. And the exponential mechanism is simply sampling a parameter according to roughly exponential to this formula, which is almost the Bayesian, which is almost what the Bayesian theorem tells you, except it normalize it differently. And so this is giving you a very general DP algo using Bayesian sampling. So in some sense, you can think in statistics, we already know how to come up with a DP algo. You can just do a MCMC. Yeah, so at the end, I will just give you a more realistic example. Turns out you can merge differential privacy with deep learning very well. So I give you an example how to, let's say you have a database of number, a database of image and the corresponding number, and you want to train an algo that given the input output, what is the number? This is the MNIST database. So and the question is, how you can train the model of predicting number privately. Namely, you don't want to leak out the information about those images. So what you can do is you just come up with a neural network that map image to the prediction. For example, you can just define the utility function to be the KL divergence between the true output. Say xi is the ith image in the database with the label yi. Then you just define the utility function to be KL divergence between yi and the prediction of the neural network. And then turns out what you can do is you just need to do gradient descent plus noise. The only difference between the stochastic gradient descent is you need to make sure the gradient is small. So the algo will do something like this. You start with some initial parameter, let's say some random thing. Each step you randomly sample image in the data set. And you run the gradient descent. namely the standard gradient descent is doing this. Theta becomes theta minus. This is the standard gradient descent. You look at the ith image, you look at the utility function, and you go towards the negative gradient direction. But in order to make anything differential perfect, remember we need to add a noise. That's why there is an extra noise term here. Yeah, let's say H is the step size. The only difference between the standard algo and DP algo is this extra term. Imagine if imagine you have one image that is an outlier that make the gradient very large. Then in some sense, you don't want to leak out that information. Because if you just run this algo, then theta will essentially just becomes gradient of UI theta. Then in some sense, you are leaking out the UI in some sense. So what the algo is doing is whenever the gradient has the lump too large, then you will multiply by some number such that it normalizes the lump to be smaller. So this is the only difference in the algo, and then you output theta. And turns out by picking a correct neural network and choosing parameter correctly, it's easy to get the accuracy pretty high even for this problem. But let me explain why you expect this is possible. So usually in deep learning, what happens is you usually only need to do few parts of the data. Since each time we only take one data, so you should imagine T is roughly n. And because we are keeping the data, you can prove this step have epsilon delta is roughly this step have epsilon delta roughly roughly constant, and this is very tiny. This will be tiny number if you choose parameter correctly. But because we sampled each step, we randomly sample a data to do this step. So the whole algorithm have epsilon delta is like 1 over n. Epsilon is roughly like 1 over n for each step. And because there is n step, it will multiply by square n. So you can imagine epsilon is like 1 over root n. So this is saying if you have enough data, then this algo will have epsilon small. And that's why you should imagine you are able to train a neural network to. In general, if you have large enough data, you can almost always train a neural network to solve the problem. Yeah, anyway. Yeah, that's it. Any question?
May I ask questions about like this exponential mechanism method? It occurs to me that seems to be using the idea. It feels like something called a Boltzmann distributions, right? If you have some probability mass functions, like a probability density function or mass function proportional to exponential of something. So it behave like this Boltzmann ensemble ways that you have like utilities behave like this something. I think people sometimes call it potential function or something, and then that gives you a way to think about that. So is that have something to do with that?
What you want, you can think it that way, but I guess for me, this connection only shows any algo for that problem can be applied here. But I think in terms of privacy guarantee, then I think it's just a coincidence.
I see.
The reason of this, basically, you can imagine how to prove this. Is just, the proof is just one sentence. It's just saying when D change, then U changed by some number. So the distribution just changed by some number. Yeah, so there is really nothing to prove here. But the funny thing is, all the tools in statistics applied for that thing can be applied here.
I see. And just one another note that I think like previously you also show a very beautiful, interesting result that when you are kind of subsampling, I would call it subsampling, like originally you have a large and then you have this probability P, that's subsample, smaller sample, right? And then you apply this epsilon delta, and then that gives you like, then you can boost the privacy, like the protection to be epsilon T and like delta P, right?
Yeah.
I think, is that already give us a way that, oh, if you suppose you start with a huge data set, but a simple way is that, I can always pick a larger, more epsilon delta private algorithm. I can pick a large epsilon and a large delta, but then when I final release a final answer, I always do a subsampling and then to do a small sample and then apply the algorithm. And then that's what I'm going to release. And then because of that features, that this is going to become like when P is very small, that's going to guarantee that the output is going to be very, very private.
Yeah, but at the same time, when you subsample too much, then the accuracy is losing. But
right.
it is in some sense a boosting in some sense.
Mm-hmm. Yeah. Right. But if you subsample, so suppose you have start with a huge like trillions of sample size, and then you can still subsample say medians and trillions relative to the median. The P is still small, but then your estimate, it is a stochastic error is small, and
and that's why in practice people can use this type of thing.
I see.
The data is large enough.
Okay. Yes. Other questions for Hinte? I also have actually another more like just curious that I think differential privacy is a quite strong sense of protections, right? So that's why in a sense it's more like the motivating example you were giving at the beginning is more like, oh, suppose an attacker knows everybody except for one individual, and I think that also translates into the case that we are thinking about two data sets that only differ by at most one entries. I wonder if people say, if I can because that's a very strong sense of protection. So I was thinking that do people have wondering that suppose I have say, well, I'm going to release that, like relax that assumption to be like a proportion of P supposed to attack at most knows like the P individuals. And then that kind of like we can assume that the attacker is randomly select P, like suppose this attacker is kind of strong. So or kill a small fraction or some fractions. And
I think that probably I think someone studied that, and that also makes sense.
Mm-hmm. Yeah. I see. Yeah, and then because I think that's a weaker sense of the privacy protections. Yeah, so perhaps can still give some interesting bounds or like the control, because I can see that when you introduce a noise that could gives you some like basically you have the original sampling and statistical error, and then on top of that you have this error coming from like the privacy protections.
Yeah.
Other questions? Okay. I think everybody's very eager for the weekend. It's like the weekend just before the Thanksgiving.
Good Friday.
Yeah, Friday afternoon. People are planning for maybe virtual parties.
Yeah. Thanks for inviting me.
Yeah, it's great to have you here. Yes, it's a very interesting topic, especially I think all this differential privacy. Yeah, I think it's a hot topic, and somehow I think we should have more understanding and more work on that. I know there are a couple of people working on that, but yeah, maybe we should just have more things like that in the future. Yeah, it's an very important, interesting topic.
In fact, they haven't figured out how to do 2025 census.
They haven't.
The trouble is this. There is two types of census. One type of census release not only the age, sex, and races. They also release way more information like salary or those kind of stuff. And they have trouble figure out how to release those in a DP way.
I see. Yeah.
And there is a professor in Utah working on this.
Okay. Wow.
Yeah,
I can see that's a very challenging thing, especially when they are releasing so many tables and
that is difficult.
Right.
Yeah, thank you.
Okay, great. Thank you so much for the talk. It's great talk.
Yeah, how to. Yeah.